Hello everyone, welcome back to learn the Axially loaded member. In this lesson, we will study the design method and the procedure of build-up axially loaded compression members. Previously, we have introduced the definition of a build-up axially loaded compression member. Build-up member is a member which is made up of two or more individual sections connected by lacing bars or button planes. The common cross-section of the individual section in a build-up column can be an angle, channel, or I-section. The lacing system used for connecting the individual section can be a lacing bar made up of an angle or button plant made up of a steel plant. According to the type of connection between the column leaves, the build-up members may be classified as laced columns and button columns. See Figure 15 and Figure 16. Next, let's study the concept of the real axis and the virtual axis of the build-up compression member. As shown in Figure 17, we usually define the central axis perpendicular to the plane of the column lip as the real axis of the build-up member, which is represented by the y-axis. And we define the central axis perpendicular to the plane of the lacing bar or button plant as the virtual axis of the build-up member, which is represented by the x-axis in the figure. Since the distance between the axes of the two column lips can be adjusted, it is easy to achieve equal stability for a build-up member along with the directions of two principal axes. Before explaining the design methods of the build-up axially loaded column, we need to understand the concept of the equivalent slenderness ratio first. For a build-up column, global buckling may occur about the real axis y or the virtual axis x of the member respectively. When the build-up column buckles about the virtual axis x, a large shear deformation may occur in the plane of the lacing bar or button plane due to the low shear stiffness provided by the lacing system, which further reduces the stability bear capacity of the whole member. Therefore, when calculating the overall stability capacity of the build-up column about the virtual axis, we usually use an increased slenderness ratio to consider such a shear effect. The increased slenderness ratio is usually called the equivalent slenderness ratio, which is represented by lambda 0x. Since the mechanical calculation models of the laced column and the buttoned column are not identical, different formulas are used to calculate the equivalent slenderness ratio. See equation 4-12 and equation 4-13. In equation 4-12, lambda x is the slenderness ratio of the build-up column about the virtual axis. A is the overall gross cross-sectional area of the build-up column. A1x is the sum of the gross cross-sectional area of the diagonal lacing bars. In equation 4-13, lambda 1 is the slenderness ratio of a single column lip about its central axis 1-1. Which is parallel to the virtual axis of the column section. Figure 21-22 shows the 1-1 axis of the column lip and the calculated length L1 used to calculate the slenderness ratio lambda 1. As can be seen in the figure, for a lacing column, L1 is the chord length between the two successive joints. For a button column, L1 is the night distance between two button planes. For the build-up axially loaded columns, the calculation formula of the overall stability about the real axis is the same as that of solid web columns. However, in the stability calculation of the build-up column about the virtual axis, the equivalent slenderness ratio lambda 0x must be used to derive the corresponding stability coefficient phi x. In addition, Despite the necessary calculations described above, we also need to ensure the stability of a single lib in the column to prevent buckling occurred on the column lib before the instability of the whole column. In order to satisfy the above requirements, the following rules are given in the code. For a laced column, the slenderness ratio of a single column lib should be less than or equal to 0.7 times the lambda maximum. For a buttoned column, the slenderness ratio of a single column lib should be less than or equal to the smaller value of 40 and 0.5 times the lambda maximum. In the formula, lambda maximum is the larger value of slenderness ratio lambda y about the real axis and the equivalent slenderness ratio lambda 0x about the virtual axis. Next, let us study the procedure of designing a build-up axially loaded column. The specific design steps are as follows. Firstly, select a trying section according to the requirement of the overall stability of the real axis y. In this step, assume a value for the slenderness ratio about the real axis and check the corresponding table in the design code to obtain the value of stability coefficient phi y. Then calculate the required cross-sectional area according to the equation 4-19. After that, select an appropriate type of sectional steel as the trying section of the column lib based on the obtained cross-sectional area A. Then verify the overall stability of the trying section about the real axis. Second, determine the distance between the two column libs according to the principle of equivalent stability. In this step, one needs to first determine the slenderness ratio of the whole cross-section of the column about the virtual axis according to the equivalent stability conditions, namely lambda 0x equal to lambda y. Then calculate the radius of gyration of the column about the virtual axis. Finally, determine the distance between the two column libs. According to the approximate relationship between the radius of gyration Ix and the width of the section. Third, verify the overall stability of the column about the virtual axis. If the stability is not satisfied, adjust the distance between the two column libs to ensure the stability bear capacity. Fourth, at the same time, the slenderness ratio of the single lib should be calculated and checked as well to ensure the stability of the single lib. Fifth, design the lacing bar and battle plan. In the design, the lacing bar is generally made up of a single angle, which can be treated as an axially loaded compression member, while the button plant is usually made up of a steel plant, which can be treated as a combined axial and bending member. The specific design method about the lacing members can be referred to as the relevant design codes. In this lesson, we have studied the design method and the procedure of build-up axially loaded compression members. See you next time.